All right. Hi, everyone. Welcome to PQ. This is an awesome assignment. This is a very, very different assignment to Boggle. In Boggle, you went ahead and you implemented a large program with many, many moving parts, with like very complex sort of recursion parts to it. This will have very little, if not no, recursion whatsoever. In this assignment, you're going to be implementing a priority queue in three different methods. One is with an internal array, one is with an internal linked list, and the other one is with a binary heap. Now, at the beginning of the class, we introduced all of these various data types, right? ADTs. And we sort of told you, they're really, don't worry exactly about how it works internally. It just sort of works in this manner. And we didn't worry about, what the inner workings were. Now, as the class advances and we sort of become, more serious in our programming, now we're actually looking at how things work internally and how we can sort of utilize their internal structure for different tasks, right? So all three of the different types of priority queues have different sort of benefits and costs to them. Some enqueue really quickly, and some are really slow at dequeuing. Some use more memory than others. Some, there are many different reasons for one or the other, and understanding and being able to master how the inner workings are is super, super useful. Any questions before we start? For the outline we're going to do today, we're going to be first going over the handout, looking over the three implementations, understand exactly what we're asking of you. Before that, we're actually going to look at, sort of play around with the sample jar to sort of see exactly what's being asked of us. And then we're going to actually look at what these things look like in their inner workings. We're going to be drawing some stuff on the board. We're going to be using a couple of visualization tools to sort of understand exactly what's going on. Before you sit down and start coding this assignment, I definitely recommend that you internalize and understand what you're going to be doing. What is it that you want to do? What is it that you need to do? Because there's actually not all that much code that you're going to be writing for this assignment. All the different functions actually can be written in a very succinct manner, but they are very sort of profound in what they do, and it takes a lot of forethought to understand exactly how to do these things. And so I definitely recommend that before you sit down and start coding away, it's sort of like writing an essay. If I ask you a question about, what are the causes of World War II, you don't just sit down and start writing, I think that the cause was because of, I don't know what's going on, right? You sit down, you think, and then when you can give an informed answer. Same thing with coding, particularly with PQ. There's not too much code, but it's definitely very, very thoughtful code. All right? So this jar is over on the website. You guys can check it out. A lot of this sort of interaction with the user is done for you. In reality, you don't have to worry about that. This assignment is really, really useful, and you're going to learn how to work with this interface for testing your code and for developing. So when we start, we go ahead and we can choose which one of the three we want to start out with array, linked, and heap. Those are the three types. You can also go ahead and extend and make your own extra, but that's an extension that you can choose to do. Now, all three, when you're working with them, work in the same way. So for example, even when you don't know what the array or the linked list or the heap work, they all will work in the same way. So we start with the array, and I'm going to enqueue. So I write E, and it asks for a value. The value I'm going to write is Sam, and the priority is going to be 4, right? So if I go ahead and I print Sam, it goes ahead and prints Sam 4. Now if I go ahead and enqueue something else, I'm going to enqueue Jane with priority 3. When I go ahead and print out Sam 4, Jane 3. Now, if I go ahead and I peek, it's going to return Jane because Jane has a higher priority. And then when I go ahead and dequeue, it's going to dequeue Jane first. Print out again, Sam, dequeue Sam. All right? Any questions about this? So you're not actually writing a lot of this code. We're going to be looking at the starter code in a little bit, but you're actually going to be working with the enqueue and dequeue functions, and not about reading what the user is inputting, being robust about that sort of stuff. Does that make sense? All right, cool. Now we can go ahead and jump into the handout. Can you guys read this? I think it's a pretty good font, right? All right, awesome. Now, you're going to be writing a priority queue. Now, what is a priority queue? Yeah. Okay, awesome. So it's a collection where things are stored given a priority. What are main things that I want to do with a priority queue? Someone else.
The one with the highest priority is out first.
Exactly. So we want to dequeue things with highest priority first, right? Awesome. What are things with high priorities? Things with high numbers or low numbers? Low numbers, right? That's something that always confuses me. That things with low numbers have high priority. All right? It's kind of confusing because it's high and low. But you basically have to think about it that way. Whoever is lower comes first. All right? Okay, awesome. I can dequeue things with low priority. What are some other main things I want to do with a priority queue? Just dequeue things? What else? You can enqueue, right? You can put things with certain priority. Awesome. Anything else? Change priority, right? That's a big one, right? I want to be able to say, you know what? If I'm writing a priority queue for, a hospital emergency room, and someone who first came with a cough now is having a seizure on the floor, I want to change their priority real quick, right? I want to increase their priority. I want to attend them earlier. All right, awesome. Change priority. Anything else? So I also want to peek, right? That's a big one, right? Sometimes I want to say, who's the person with the highest priority without actually removing them, right? All right, so this is sort of like a general outline of what the priority queue is going to do for us. There are going to be 6 main files, that you're going to be sort of implementing and submitting for this assignment. The array priority queue, link priority queue, and heap priority queue. We go ahead and we provide this to you guys. Just a heads up, this is going to be a pair assignment. You can work with someone else in your section, but only someone else in your section. All right, like previous assignments. Awesome. So we talked a little bit about the priority queue collection, about how it works, about how things with lower numbers have higher priority, and how you want to sort of enqueue and dequeue things depending on the priority. So we're going to sort of skip over this a little bit. Our task is going to be implementing all 3 versions of the priority queue. All right. In each of these implementations, we want you to actually write what the big O for enqueuing and dequeuing is. This is the first time for an assignment that you're going to be sort of working with big O, so definitely brush up on that. All right? Awesome. Now, there are 3 main priority queue implementations that we're going to ask you to do. Right? First one is going to be the array priority queue. All right? It's actually the simplest one. In the array priority queue, you're going to be using an unsorted array as an internal data storage. All right? So the array itself is going to be unsorted. The only private member variables this class is allowed to have inside it are a pointer to your internal array of elements and integers for the array's capacity and the priority queue's size. All right? The elements of the array are not stored in sorted order internally. As new elements are enqueued, you should simply add them to the end of the array. All right? Does this make sense? So we're not actually going ahead and sorting the array every time we enqueue. It's actually going to be unsorted, all right? Which may be a little bit confusing. Right? So here, if we add, for example, Z9, it's actually going to come here at the end at 6, right? It's relatively simple to enqueue things, all right? Now, when we're dequeuing, this is when the fun begins. We actually have to search the array to find the smallest element. Then we're going to go ahead and return and remove it. So clearly, enqueuing is really quick. What's the complexity of enqueuing? Of 1, right? We're just putting something at the end. What's the complexity of dequeuing? Of n. That's not particularly good, right? But this is this implementation. Here we can see like the internal array of state of an array priority queue. So here, for example, if someone calls dequeue, what does that look like? What do we return? We return T, right? Because T has the highest priority, the lowest number, right? It's a little bit confusing. So we return T, and then the state of the array is going to be as it is with only these numbers. Now, what if I dequeue once more? What do I return? No, T's out. It's going to be B, right? Because B has the lowest number, highest priority, right? So it's actually going to be just X5 and then A8, M5, Q5. Does that sort of make sense? All right. Any questions about the array priority queue? Yep. All right, so the question was, if you remove something from the middle, do you have to move everything over? You do, right? No?
Is it sorted?
Is it sorted? No, it's not sorted.
Do you need to move it over?
Do we need to?
Let's say we're doing,
Oh, yeah.
let's say we're
Interesting.
doing min here. Well, bad example. Let's say if the min was
Was A.
8.
Yeah.
Okay, if you remove that one, we could move everything back,
Mm-hmm.
but it's not in any order.
So what could we do?
So what could we do?
Do what?
What's that?
But if we move the next one, we're going to have a hole.
Say a little bit louder. Move the last one. Yeah. Move the last one into the spot where it goes, and no other movement becomes constant time.
Nice. Awesome.
Awesome that way.
Does that make sense? And so when we're removing something from the middle, since it's unsorted, as Chris pointed out, I'm just repeating this for the camera. Since it's unsorted, you don't really have to shift everything over. You can just shift the last one into that spot that you removed, and that takes constant time. Does that change the complexity of dequeuing? Why? Exactly. You still have to find one, but it does make it a little bit quicker, right? Which is pretty cool. All right. Awesome. Now we're actually going to look at the starter code for the array priority queue, right? So if we look at the H file for array priority queue, we go ahead and we provide all of these sort of public functions that you actually have to fill out for yourself, right? You also have the ability to include private ones. We were very specific about what you can and can't include for the array priority queue, and so definitely follow those guidelines. If we actually look at the CPP file, you'll see that everything is very nice and it's very clear exactly what you have to code, right? Now, you definitely can go ahead and add private functions and add them to the class. You're welcome to do this. Just don't change any of the public methods, right? Because that's how we're going to be grading you. That's how we're going to be running it, and that's how the sort of the console interfacing system interfaces with your priority queue. Does that make sense? All right. Any final thoughts or questions about the array priority queue? Seems pretty simple, right? Yeah? All right. Awesome. Now we're going to move on to the linked priority queue. All right. This one's a little bit more complicated. So the second one that you're going to be implementing actually uses a sorted linked list as the internal data storage. In this class, we only allow you to have a single private member variable, which is going to be a pointer to the front of the list. All right. The elements of the linked list are stored in sorted order internally. So, as a difference to the array priority queue, in the linked list, we do want them to be in sorted order. All right. As new elements are queued, you should add them at the appropriate place in the linked list so as to maintain the sorted order. When dequeuing, you do not need to search the linked list to find the smallest element and remove/return it. It will always be at the front of the list. Awesome, right? The implementation is harder to write than the array implementation, and queuing to it is slower, but is much faster for dequeue/peaking and has better overall performance. The following is a diagram of the internal linked list state of a linked priority queue after queuing the elements listed on the previous section. All right. What is the complexity of queuing things? O of n. Why is it O of n? Exactly. You have to go ahead and insert it at the right priority, right? Which may require you to go ahead and loop through the entire linked list. Now, what about the complexity of dequeuing? O of 1, right? So dequeuing is going to be really quick, right? So as we can see, like just comparing this one with the array priority queue, they're both kind of flipped, right? The array priority queue was really quick at queuing, but really slow at dequeuing. the link priority queue is going to be really quick at dequeuing, but slow at enqueuing. All right. So as you can see, different implementations, even though from the surface they both do the same thing, have drastic effects in the way that they run and the complexity of their code. All right, which is, I think, pretty cool. Now, you're going to be working a lot with pointers and with node pointers, and so one of the complex parts about this particular implementation is actually inserting nodes in the proper place when enqueue is called. You must look for the proper insertion point by finding the first element whose priority is at least as large as the new value to insert. Breaking ties by comparing the strings. All right? Does this make sense? Breaking ties by comparing the strings. What does this mean? Exactly. So to repeat that, if they're the same priority, whichever string comes alphabetically first is the one that is going to go first. All right? Now, all of these priority queues have as their values strings. All right? They're always going to be strings. So that's not something that we need to worry about. Now, so with that in mind, let's say that this is the current state of our priority queue. And I go ahead and I insert T5. Where does that go? Actually, this priority queue, there's something wrong with this priority queue. What's wrong with this priority queue? Actually, no, it's right. Never mind. Let's say I insert T5. T5. Where does it go? After the Q, right? But before the X, right? Just because T goes, in between, alphabetically between Q and X. Now, how do you check this? Strings actually, you can compare them if one is greater than the other. All right. This exists for strings, which is pretty useful, pretty cool. All right.
Does it handle it for if the strings are different sizes?
Does it handle? Yes, it does. Yes, it does. So the question was, does it handle for strings of different sizes? Yes. It's actually quite robust. You can look into this in C++ strings, how they compare. Yep. No. That's a great question. So the question is, do we have to search through the entire array to break ties with the one that is alphabetically comparing strings? Chris, is that something that we want to do or not?
I'm sorry, I didn't hear.
Do we want to? So for the linked priority queue, we're actually breaking ties in terms of the string itself, like comparing the string. Do we want to do that as well for the array?
Yeah.
Yeah. All right. We're also breaking ties for the array. All right. Good question. Exactly. So for DQ, you actually have to check them all, right? So even if two nodes or two elements, two PQ elements have the same priority, you always want to return the one that alphabetically comes first, right? So for example, all things considered, me, I'm Anton Apostolatos, I win above everyone, right? Just because my name's with A, right? So moving on, here, so we see, so as you're saying, inserting a new node is really tricky. We kind of showed this in class, but we have to actually stop one node early so that we can adjust the next pointer of the preceding node, right? So for example, here, let's say that we want to insert value O with priority 5. Where does that go? Where? After M, before Q, right? Before looking at what we do down there, what do we want to do if we want to insert O? What is the procedure? We make a node. So we have a node that has O and it has 5 in it. Awesome, we have a node. We have a node stored in the heap. Now what? Yep. Make a temporary pointer to what?
To the value of the next node.
So which is what here, for example? If we have O, right? We're trying to insert O right here.
So you make a pointer to the value for Q.
Okay, so we have a pointer to Q. Now what? Where? So we have this pointer in the stack. Like we just have it in memory. What do we do with this node, right? Because this node has a value and a pointer. What do we want that pointer to point to? To Q, right? So we actually want to have that pointer point to Q, right? The issue is that as we're looping, we're only ever going to, like, if you do this, you know, the naive sort of regular way, you're just going to be looping, passing in, you know, while, you know, node equals, you know, doesn't equal null. You're just going to keep looping, right? Until you find the spot where, you know, oh, Q equals 5 is of less priority. I want to insert it here, right? Now, the issue here is that you want to have m equals 5 point to your new node that you created, right? Which is O5. How do we do that? Because we don't have a back pointer from Q equals 5, right? Q5, sorry. But if we don't have a back pointer, we can't be like, oh, this is the guy right before Q. Awesome. How do we do that? Awesome. All right, I'm going to repeat that. So we're going to keep the last one in a temporary variable, right? So what would looping look like? So we'd start here, right? And we'd have let's say we have a current. And then let's say we have a previous, right? So at first the previous is going to be, let's say, head. Now as we loop, we're going to be passing them both like this. Now once you find in current that this is of lower priority and you want to insert in between these two, you create your new element. And you make this new element point to this current one, right? And then you're going to have the previous one point to your new element O. So that way we're inserting it into the linked list. Does that sort of make sense? Otherwise, if we're just looping, you know, with one pointer going through them all, then it's going to be really tough. Actually, it's going to be impossible for us to then go ahead and have the linked list be sort of complete. All right? Question. You can create an arbitrarily large amount of pointers, as many as can fit in your memory. Yeah. Not that you will ever want to, I hope. Any other questions? Yeah.
So essentially you're making a trailer pointer and a current pointer?
Exactly. So we're pretty much making a trailer pointer, right? It's sort of like our previous sort of pointer as we keep looping, right? Because then it's going to be very easy to sort of connect the chain. All right? So as we can see, this is what they kind of do, right? So once the current pointer shown above points to the right to you can insert the new node shown as below. We're going to actually supply you with a list node structure, all right? Each list node structure, we're going to look at this in a little bit, stores a string value and an integer priority in it, all right? And a pointer to the next node. You should use this structure to store the elements of your priority queue along with their priorities, all right? So if we look at Qt, all of your entries are actually going to not be strings. They're not going to be integers. They're actually going to be PQ entries. And PQ entries are actually a struct that we provide for you. It's really simple. It actually just stores a value and a priority. All right? So if we're creating a data structure of something as our internal representation, we wouldn't make it of strings. We wouldn't make it of integers. We'd make them of PQ entries. So if we look at what the PQ entry has for us, it basically has a simple constructor and then a bunch of operators. So you can compare sort of different PQ entries. All right? So before we were talking about comparing things, you know, breaking ties in terms of the order of the strings when the priority is the same. Does the PQ entry do that for us? It does, right? So when we look at, for example, the less than operator, right? It returns if the priority of the first is less than the priority of the second, or they have the same priority, but the priority of the value of the first is less than the value of the second. All right? So it actually does that for you. So you don't need to worry about that. Does that make sense? So that's super useful. And so for a linked priority queue, this looks very, very familiar. It actually is almost identical to your array priority queue because the class itself, the public functions, are all pretty much the same as the array priority queue. All right? Once more, we're going to be asking you to go ahead and include the big O of NQ and DQ. All right? Any questions about the linked priority queue? Yeah.
Was this for like the comparisons that you were
Uh-huh.
doing? Should we do the like include PQ entry and like our like the array or the linked list?
Should we do include, I believe that that's done for you. Is that what you were referring to?
Done for like, oh, okay, so that dot H has the
Yeah, it includes it. Yeah, so if you for example, if we go here into the CPP file, right, and we go into like the array constructor and we say PQ entry temp equals PQ entry. Sorry, new PQ entry. That works for us. All right, doesn't shout at us. It actually is a valid PQ entry. Does that make sense? Cool. Awesome. Great question. Yeah.
And we're using PQ entries in all three.
Yes, we're using PQ entries for all three. Yep. Good question.
In
Yeah.
the header file, it mentions like refer to vector priority queue.h.
Vector. Where does it say this?
Oh, so just go into one of the header files, like the array priority queue.
Uh huh.
Oh,
The H file. Sorry. The array priority queue.
Yeah, and then maybe go into the heap priority queue and .h. So there's like 4 documentation of each member C vector priority queue.h.
Oh, interesting.
What's that file?
I believe that is just an extra comment that we should have removed.
Oh, okay, right.
Yeah. Don't worry about that. I don't think. Do we have that? The vector priority queue. Here it says for documentation of each member, see vector priority queue.h. I don't think that's sort of a comment that comes from previous iterations of this program. Good question. Good catch. All right. So the actual documentation for these, if we look over, we're going to actually look at these in a little bit. It's all here. This is the documentation you need. All right. We're actually going to be looking at these right now. These are all the operations, and this is everything that you have to code. Okay. Any lasting questions about the linked priority queue? Does it sort of make sense what we have to do? Does it seem like a tractable problem? Yeah, right? Doesn't seem too bad, right? Now comes the bad boy, the heap priority queue, all right? So the heap priority queue as the internal structure is going to be using the binary heap, all right? So as internal variables, we only allow you to have a pointer to the internal array of elements and integers for the array's capacity and priority queue size. This is very, very similar to your array priority queue, right? Which we only allowed you to have these 3 variables. Now, Chris went over this in lecture on Wednesday. And if this is something that it's a little bit confusing to you right now, or for people at home who are watching the video, you're a little bit confused by this, definitely look at those lecture slides, and acquaint yourself with what's going on. Because trying to write code for the heap priority queue without being comfortable with how it works and why it works is going to make your life, really, really difficult, right? Knowing it is going to make, it's half the battle, understanding how the binary heap works, right? So as Chris pointed out in the lecture, for every index I, there's 2 children, which are going to be at I times 2 and I times 2 plus 1. Parent indexes always store more urgent priorities than their child indexes, right? So if we look at here, what are the 2 children of T? What was that? M and B, right? Do M and B have lower priority than T? Yes, they do, right? As they should. That's something important about the binary heap, right? So you have highest priority things at the top. What are the children of M? X and Q, right? Awesome. Just because 2 times 2 is 4, 2 times 2 plus 1 equals 5. What's the parent of A? What is the parent of A? It's going to be B, right? Because 6 divided by 2 is going to be 3, right? Awesome. Cool. We're going to go ahead, and this is something you can do. Skip the 0th sort of index, right? Now, a lot of people, they look at this and they say, why are you doing this? And the reason is simple. It's because the math itself actually works itself nicely when we started the first element, right? We could potentially use it. But in reality, when we're not using the zeroth sort of element, it actually doesn't increase the amount of space our program is using by a lot. It actually increases it only by a constant amount, which is 1 PQ entry, which is something that's reasonable. We can bite that. I can accept, having to store one more PQ entry amount of memory just to make my life a little bit easier. That's an optimization problem that we've sort of decided for ourselves. And we said, that's fine for us. Does that make sense? So what's in that zeroth element? It doesn't matter. All right? Now, something about the heap, the binary heap that makes it super cool is that where's the highest priority element going to be at? At 1, right? It's always going to be at the top, at the root, right? So that's going to be really cool and really sweet and really quick, right? Now, enqueuing involves sort of placing it, basically involves the bubbling sort of technique. We're going to look at this right now in terms of what the handout says and how it explains things, and then we're actually going to be using a visualizing tool, all right? So if you're a little bit confused and have a hard time visualizing this, that's fine. That's okay. When we're adding something into a heap, we're actually placing it into the first empty index. So here we're actually going to be placing it here, 7, right? Now, we're actually going to be percolating up and bubbling up. What does this mean? It means that we compare that element to its parent. In this case, what's the parent of B? It's Y, right? Why is it Y? Exactly. 7 divided by 2 is going to equal 3, right? And we compare it to its parent. If it has a higher priority than the parent, we switch, and then we keep bubbling up. If not, then we stop the program and enqueue is done. It's at its correct spot. There are actually some formal proofs which are pretty neat about why this is the case. On your off time, I definitely recommend, if you're interested about this stuff, to look that up. There are Wikipedia articles and papers and everything about why bubbling up and bubbling down work, and it's definitely really cool. Like, you should definitely check it out and impress your friends and your parents. So removing an element is kind of similar, right? So we said that when we remove something from a priority queue, we want to remove the element with the highest priority. What's the case in the binary heap? Where is this? In the first element, right? So we're going to remove the T, right? So we remove the T. We remove the T, and now we have that spot empty, right? So what we actually do then is that we move the element from the last occupied index. In this case, it's going to be the 7th thing, the B, which we inserted here at the top. We're actually going to put it in in its place, right? Which sounds kind of weird. But then what we do is we bubble down. And so we compare it with both its children. So if we place B4 into the first spot, right? So we place it here. We're going to be compared to its two children, which are M5 and Y3, right? Between M5 and Y3, which one has the highest priority? It's going to be Y. So we're going to actually push Y at the top, right? As we do here. So we bubble it down and we compare Y3 with B4, right? We switch their spots. Now what? What's the next step? Are we done? No. We have to keep bubbling down. So we compare B4 to its two children. What are the two children of B4? It's A8 and no other, just A8. Does A8 have a higher priority than B4? No, it does not. So we're done. All right. So NQ and DQ take log n time to perform on worst case, but there actually takes O of 1 when like Chris talked about this a little bit in the lecture, but actually when you have like random numbers and you're trying random things, on average it's O of 1, which is really quick and really awesome, and much better by leaps and bounds than the array priority queue and the linked list priority queue. All right. If nodes, so here we go over this a little bit again, but if nodes ever have a tie, we can break ties by comparing the strings themselves, right? we compare strings using the standard relational operators, which is less than equal to, greater than equal to, equals, and not equals. All right. As it says here, do not make assumptions about the length of strings, right? Something you have to keep in mind. Now, how do we change the priority of something in the priority queue? How do we change the priority? What do you guys think? Yeah. So when you change the priority, you're actually changing the importance of something, right? Like how important it is. So sometimes when you do this, you're going to be changing its position in the tree, right? Because if we go in and I call change priority A1, right? What's going to happen? What's the tree going to look like? Exactly. A is going to go all the way to the root. So how do you guys think that we can go ahead and change the priority of something? What was that? So careful when you use the word dequeue, right? Because when we're dequeuing from a priority queue, you're actually removing the first element from the priority queue, which isn't exactly what we're doing, right? Because we're changing the priority of something that's within the priority queue itself, right? So actually, changing the priority of an existent value involves looping over the heap. So we're actually looping over the heap and we find this value, right? Looping is going to take O of n time. Once we find it, we are going to change its priority and then actually bubble it up. Something that is sort of specified about the change priority function is that you can only increase something's priority. You can't decrease it, all right? So that's why you're always going to be bubbling up. Does that make sense? Because it can never be more down in the tree. It can only be more up. Yes, it is man-made rules. It's a rule for our implementation. Yeah.
What is the meaning
For capacity of 10? Awesome. So the question is, what is the meaning of capacity? Does anyone have any intuition as to why we want to store the capacity of something, of this array? Yeah. In case you need to double the size, right? So we know how many elements are in our array, and we know how much memory we have, like in terms of like things that we can store. Once these are equal, you need more, and you start enqueuing something new, you need more space, right? And so then we go ahead and we can increase the capacity by 2. We always double in size. Create some new memory, copy things over, and then increase the capacity, right? So now we have space for more stuff, all right? And the value of the capacity is here, you mean? The capacity is 11. Interesting. I don't really know why that's the case. That may be a error on our end. I believe the capacity should be 10. Good catch. So the question was whether or not the 0th element is actually a part of the capacity or not. That sort of depends on how you want to internally set it up, right? You can have the capacity include the 0th element, and you can have it not. You just have to make sure that your math works out and that you're actually increasing the size of the array when you need it. Yeah, right. So yeah, either one is fine, right? Either one is fine. All right. Any questions about the link priority queue before we keep going? So we're actually going to start working with a heap visualization tool that Chris is going to go over tomorrow, but we can sort of get used to it. This is in the lecture slides from Wednesday. And this is super useful, all right? So this actually has the internal representation of a binary heap, and you can work with it, and you can like test it out, and it's really cool. So the way this works is that it's sort of really simple. It assumes that the priority and the value are the same thing, all right? And so basically, the priority of something is going to be its value, and that's sort of really simple. So if I insert something, priority 3, sort of value 3, it's going to go ahead and insert it at the root, right? Now, what happens when I insert something that is of priority 5? It becomes its child, right? Left child or right child? It's going to become its left child, right? Because binary heap always fills from left to right, right? So if I insert something priority 5, go ahead and insert it there. Awesome, right? Now, let's say I insert something. I'm going to insert a bunch more things, right? I'm going to insert an 8. There we go. Sweet little animation. It compares 8 and the 3. It doesn't bubble up. Now let's say I go ahead and insert a 2. What's going to happen? What's going to happen? What's the first thing that's happening? 2 goes to where? Exactly. So 2 is going to actually go into the child of 5, right? So it's going to go in the 4th spot, right? Then what? Then it bubbles up. What does bubbling up mean? What do we compare this guy to? We compare it to 5, right? At the second index. So we go from 4th index to 2nd index. We can compare it to 5. Is it higher priority than 5? Yes. So we bubble them. We switch them. And then what? Are we done? No. We keep bubbling up, right? So then we go ahead and we grab this, the second, and we compare it to the first, right? So here we're going to have a 2. Here we're going to have a 3. Which one's higher priority? 2. So we bubble up, and then we're at the root. We're done. Let's try this out. Let's see if we're right. So inserts the element 2. It compares them. Switches them. Compares them. Switches them. And thus, it ends. All right? That's pretty cool. Pretty sweet. Now, I'm going to go ahead, and I'm going to insert a bunch more. I'm going to actually increase the speed of this thing to make it a little bit smoother. All right. Does that allow? Yeah. 15. All right. 7. Cool. So now I'm gonna insert something new, and this is gonna be like a little test. You're gonna have to tell me in which index is gonna be its last index. It's the index at the end of our enqueuing. All right. So I'm going to go ahead and I'm going to insert 7. Now, think about it for a second. Where is 7 going to go when we're done with our entire process of bubbling up? I'll give you guys 20 seconds. All right, any guesses? Yeah.
13.
It's going to go into 13. Why into 13?
Because you put it at the end of the array,
Mhm.
so that means it makes a child of 8 and then has to bubble up, and 7 is greater than 8, or less, higher priority than 8, then it's 8, right?
Which one? The
The 13, right?
yeah, 13 here.
So 7 is a higher priority than 8, and then you check it to 2, and it's not a higher priority than 2, so then 7 is 8.
Interesting. So, what is the child? So, where do we first insert 7? What's our first thing that we do? At what position do we insert it? We insert it at 14, right? What's the parent of 14? It's 7, right? It's the 8 at the 7th position, not the 8 at the 13th position, right? So we're actually comparing it to the 8 at the 7th position, right? And so when we compare it to the 8 at the 7th position, which one has a higher priority? The 7 or the 8? 7 has higher priority. So it's going to actually switch with the 8. Now we compare the 7 at the 7th position. Who's its parent? 3, right? Is 2 higher priority than 7? Yeah, so we stop. Actually slow this down and let's run this. So it's the 7 at the 14th position. Compares it with the 7, switches it. Compares it with the 3, does not switch because 2 is higher priority. We're done. All right? Okay, one last test. I'm going to add a couple more. All right. This is a tricky one. I'm going to add 4. What is the final position of 4 when we enqueue it? Give you guys 10 more seconds. All right, any answers?
Index 4.
Index 4. Do people agree with him? Does someone disagree with him? All right, no disagreeers. All right, let's see if we're right or we're all wrong. So we go ahead and we insert 4. We insert it at the spot 16, right? Which is the parent of 16? 8, right? So we're going to go ahead and look at 8. Is 9 higher priority than 4? No. So we switch them. We bubble it up. So it's now going to be in position 8, right? Remember that things with lower number have higher priority, right? Now we're at 8. 4 is in 8. Now what? Do we keep bubbling up? Yeah, right? Now who's the parent of 8? It's going to be 5, right? Now what's going to happen? If we compare 4, wait, it's going to be, so 8, it's going to be, yeah, 5, sorry, 4, sorry. 5 at 4. We compare with 5. Is it higher priority? Is 4 higher priority than 5? Yes, so we switch. So we switch the 4 and the 5. Now we compare the 4 in the spot 4 with its parent. Who's the parent of the 4 here? 3. Is 4 higher priority than 3? No, so we stop. Now let's see if we're right. We insert it in spot 16, compares it to the 8, switches them, then compares it to the 4, switches them because higher priority. Here, no, stops there. All right? Now, right now, what we're doing is we have this awesome tool that helps us understand exactly what's going on. Before, if you're confused, if you think that you don't fully understand what's going on, that's perfectly fine. That's okay. Use this tool to help you. When you're working through your code, and when you're debugging, and when you're testing, and when you're developing, definitely go ahead and have a pencil and paper, have this website up, and see, is my internal representation of the priority queue the same as this one, as the one that I'm doing pencil and paper, after, 5 enqueues, 4 dequeues, and like 7 other enqueues, right? If they're not the same, there's a bug in your code. All right? So use this as a sanity check. Yep.
So are we ever comparing like a priority with its sibling? Like for example, if we replace one of the children of the root, and it turns out that the sibling is actually lower priority than the value the priority we just replaced, we go into the siblings position.
So we actually never do that. And so the question was, do we actually check siblings when we're bubbling up? And the answer is no. And it's because we don't need to. By definition, the binary heap just says that the parent has like a lower number and thus higher priority than both its children. It doesn't say anything about the comparison of the two children, right? And we don't need that. When you look at enqueue, when you look at dequeue, they're both really quick, and they don't need us to compare children and sort of change things out, all right? That's not necessary. All right. It was a great question. Any other lasting thoughts on the linked priority queue? All right. We can actually now look a little bit more at exactly what are the functions we want you to sort of write out for this assignment. The first one is going to be enqueue. This one's relatively simple and straightforward, right? We're actually going to be adding a current value string with a priority integer, right? We allow for duplicates. any string is legal and any integer is legal. There's no such thing as an invalid value. All right? We're not going to be passing in invalid values. Now, dequeue just goes ahead and removes the element from the most urgent priority from the priority queue. We're actually going to be returning it. If the queue is empty, we want you to throw in a string exception. Does that make sense? Now, depending on your implementation, these can be really complex or really simple, right? It just depends on which of the 3 priority queues you're working on. Yeah, question?
So if everything is just being passed in as a string, then like if you pass in like a double or int, it's not gonna actually like check the value, it's just gonna check like their string value. Like if
As a value. So the question was whether, so like a value that's being passed in, can it be like a double or can it be something like different than a string? Was that the question?
well no, like it's gonna be saved as a string, but if you're passing in a number, it's not gonna actually be like checking the values of the numbers.
It's going to be looking at them as they were strings. So it's not if you pass in like 23, it's not looking at 23 number. It's looking at the string composed of character 2 and character 3 together.
Like if there's like a decimal in there, then like
It works. You don't need to worry about that, right? Yeah.
For the priority part, if we pass in a double or a float, what do we do?
For the priority part, so the priority itself is actually an int. We can go ahead and check this out. Then it's going to convert as an int when it's passed in. So you in your program, when you're, let's say that you start writing a array priority queue, right? And so you go into this .cpp, and you're writing enqueue priority is always going to be an int.
So we do not need to like pop out.
Nope, you don't need to worry about that.
If it passes a string, what do we do?
If it passes in a string as your priority, I think that the program is smart about that. Let's try that out. Let's enqueue value t with priority I, illegal integer format. You don't need to worry about that. Awesome. Yep. Let's see if we pass it in a negative integer. All right. So I'm going to pass t with negative 56. Enqueued with priority negative 56. So if I go ahead and print it out, we have t with negative 56. So your program should work with negative numbers. Where would that be? So is a negative number a higher priority than 0? Yes, because it's a lower number. Same things applies. You'll realize that generally, if you write your code well and your program, is robust, you shouldn't be worrying too much about negative numbers. It should be already working. All right. Now we can keep moving. We look at peak. So in peak, we're just returning the string element in the most urgent priority. If there aren't elements, as before, we just throw a string exception. Peak priority returns the integer priority that is most urgent from the priority queue. So this is actually kind of similar to peak, but instead we're returning an integer priority. If there aren't any elements, once more, we throw a string exception. Now, change priority. This is a big guy. In this function, we're actually modifying the priority of a given existing value in the queue. The intent is to change the value's priority to be more urgent than its current value. If the given value is present in the queue and already has a more urgent priority to the given priority, or if the given value is not already in the queue, your function should throw a string exception, right? If the given value occurs multiple times in the priority queue, you should alter the priority of the first occurrence you find when searching your internal data from the start. So we allow your priority queues to have duplicates, but then when the user asks to change the priority of one of these, whichever duplicate, whichever one you encounter first, you go ahead and change the priority of that one. Is empty returns true if the priority queue does not contain anything, and returns false if not. Size should return the number of elements. Clear should remove everything from the priority queue, should just clear it out. And we're also, similar to Boggle, going to be writing out a like a printing operator, and you can print it out in any order, but it has to be of the form value, like quote value colon priority, using these curly braces. These are really useful, and it's super useful to actually have this operator written almost the first thing that you do when you write code. And the reason is because it's really useful for debugging. It's really useful to understand exactly what the internal representation of your priority queue is at every step. As I noted earlier, the headers of every operation has to specify these, match these. Do not change them. Please do not change them. Your code will crash. It won't be working. Yep.
In the example jar file, there's a space after each comma, but in this, there's no space after.
So the question was whether or not there should be spaces after commas or not. Definitely put spaces after commas. We can actually go ahead and modify this, but good question. All right, we actually want spaces, just because it's a little bit easier to read, right? This is kind of tough to read. Anything else? Yep. What? Yeah. So as the exception that you're returning, right? You can be as vague or as clear as possible, right? You can be attempting to usually, and I definitely suggest that you do say attempting to enqueue from a dequeue from an empty priority queue, and you throw that. As long as it's string, exactly. I definitely suggest you do that, just because when you're sort of debugging your code and when you're testing it out and you find bugs, a lot of the times you're actually going to be crashing your program with you throwing string exceptions, right? And sometimes how explicit and clear you are in the text of the string exception that you're returning is going to help you debug. So it's actually kind of useful to be very clear in the exceptions that you're returning, that you're throwing. Good question. So that's roughly it. You're also going to be having a constructor and a destructor. The destructor needs to free any allocated memory, at the end of your program. So if you ever sort of ask for memory from the heap, you should definitely go ahead and free that up. In terms of helper functions, you should add other we invite you to add other members to help the implementation of all of this behavior that we've gone over. All of them, however, must be private, and they should all have a clear purpose. You should all have clear comments, and they should all make sense why you've included these new functions. Do not provide helper member functions for common repeated operations. If you do this, that's sort of style deductions right there. If you're not performing a modification of the object state, make it const. Some other constraints about member variables is don't make something a member variable if it is only needed by one function. Make it local. All right? Making a variable into a data member that could have been a local variable parameter will hurt your style grade. And all data member variables inside each of your classes should be private. So pretty much in your H file, you should only be working with the private sort of portion of it. Now, here are certain implementation details. We're not going to go over these right now, primarily because we just run out of time. I definitely recommend you read over these before you submit your assignment. But before we finish, and we also have certain development strategies. Implement these in the order that we present them, just because it's going to make your life much easier. Draw pictures, use this visualization tool, understand what's going on under the scenes and what should be the model behavior of your code. Don't panic. If things get nasty, take a break. Step back, come back to it with fresh eyes, because things, when you start working with pointers and with linked lists, can get a little bit confusing. That's okay. That's part of the learning process. And also test. Test. Right? There's a lot of places where your code can crash and it can be wrong. So definitely, try to test every possible case scenario that you can for your code. There are also some extra features that you can add, which are pretty cool. Pretty cute. Definitely, yeah. I don't know what happened there. But definitely go ahead and check that out if you have extra time. Definitely, it's an assignment you can extend, and you can do some pretty cool stuff about it. But before we go ahead and dismiss, are there any sort of general questions about the program? Do you feel roughly comfortable about what we asked you to do? Is there anything that's super big, that's a little bit confusing? that you think would be helpful to go over? So we roughly feel that we can sort of already start jumping into implementation. Right, awesome. That's good to hear. Yeah. So what's the difference between the clear function and the destructor? Destructor means I want to remove all the memory that I'm using and I'm done with, everything that I ever allocated, I'm done with. Clear says no. Clear says I want to remove everything within the priority queue, but I might still want to use it. So for example, if you have a vector, if you had a clear in the vector just removes every element in the vector, but doesn't actually, the user can still add things to the vector. In the destructor, it's done, it's over. That vector is unusable. You've cleared all the allocated memory, they can't add anything to it. All right, good question. Yep?
When is the destructor called? You don't call it so.
No, you never call the destructor. So the destructor is called when variables go out of scope. And so when you create a local variable in a function and then you return from that function, then the program itself will go ahead, your computer will call the destructor. You don't really ever call the destructor. You do, I guess, when you delete something. When you delete something, it actually is calling the destructor of that object. But a lot of the time, that doesn't happen, right? A lot of the time, it does it automatically. All right, awesome. All right, awesome. Thank you guys for coming. I hope that the assignment's a little bit clearer. I hope that you guys are sort of, I feel that you guys are well on your way to mastering the priority queue. The assignment is due next Wednesday, so definitely take this weekend to work on it. And yeah, good luck with it. Thanks, guys.